Today we are going to look at how to determine the Thevenin equivalent circuit for circuits containing dependent sources. We're going to have to adapt our strategy slightly from what we learned in the last lecture in calculating the Thevenin resistance. And the reason for that is, with a dead network, if we looked in through these terminals with the 2-volt source as a short circuit and the 6-volt source as a short circuit, we can never turn this dependent source off, and so we don't have a simple resistor network that we can simplify. So instead, we're going to have to rely on the relationship that the Thevenin resistance is simply the ratio of the Thevenin voltage divided by the Norton current. So for this circuit, let's first find the Thevenin voltage, which will be the potential difference between terminals A and B. And there are a multitude of different ways that we could approach this problem. I'm going to choose to use nodal analysis, and the reason for that is that I've worked this circuit on multiple times and I made an observation that nodal analysis is actually going to be much easier. You could absolutely do this using mesh analysis or any other circuit analysis technique that you can apply, but nodal analysis gives us a couple of interesting observations. I'm choosing the bottom node, node B, to be my reference. The reason I'm doing this is because that means that I have, actually let me go ahead and assign my other nodal voltages as well. So let's call this node 1, 2, 3, and 4. So I'm going to have a super duper node, as it were, that's going to enclose all of this, because all of these voltage sources, like for instance, the voltage source between node 3 and node 4 is connected to the super node between V4 and V ground. And since they are connected and contains ground, I won't have to do Kirchhoff's current law at supernode 1, 3, 4. I'll only have voltage relationships. And we could write those down pretty quickly. We could see by inspection that V1 is just 6 volts, V4 is 2 volts, and V4 minus V3 is equal to 3 Vx. And while we're at it, Vx would simply be equal to V1 minus V3. Now what's interesting is that none of these voltage relationships actually help us, because our Thevenin voltage is going to be V2 minus the nodal voltage at terminal A minus ground, or 0, the nodal voltage at terminal B. If we apply Kirchhoff's current law at node 2, what we get is V2 minus V1, which is 6 volts, divided by 1 kiloohm, plus V2 minus V4, which is 2 volts, divided by 4 kiloohms, is equal to 0. So KCL at node 2 actually gives us the means by which to determine V Thevenin with one equation, one unknown. So V Thevenin is equal to V2 is equal to 5.2 volts in this case. For our Norton current, let's write V Thevenin here. We can again vastly simplify our circuit analysis by thinking about things. So what I mean by that is our Norton current is, by definition, the current that flows through a short circuit we place across terminals A and B. That will be the sum of this current plus this current, according to Kirchhoff's current law, right? These two currents flow in, I Norton flows out, so we find that I Norton is 6 volts divided by 1 kilo ohm. And we get to just say it's 6 volts minus 0, because when we short this and treat node B as ground, it's got a 0 potential, plus V4, which is 2 volts, divided by 4 kilo ohms, is 6.5 milliamps. So this very ugly looking circuit actually can be solved rather trivially if you don't fall into the trap of trying to use mesh analysis and really nodal analysis for everything. Kirchhoff's current law was the only thing that was actually needed to solve this problem. So now that we know V Thevenin and I Norton, we simply take the ratio. So R Thevenin is equal to 5.2 volts divided by I Norton, 6.5 milliamps. And I believe, let me get my calculator here, so this is going to give us 800 ohms. Yep. 800 ohms. So the key here, really, is recognizing that we were never going to get a resistance of 800 ohms by trying to do resistor combinations or anything like that in this circuit. The only way that we can really analyze or determine the Thevenin resistance for a circuit like this is to calculate the Thevenin voltage and the Norton current and take the ratio. There is technically one other method, and it's called the test source method, and I'll detail how that works. So, in the test source method, what we will do is we will apply either a voltage source or a current source to the dead network and then calculate our quantity of interest. This is effectively just employing Ohm's law. You may recall from our lecture on Ohm's law that if we have a 2-terminal network and we hook up some voltage source to it and measure the current flowing into the network, the resistance of the network is simply V over I. And similarly, if we have the same network and we hook up a current source and measure the voltage drop, we would find that the resistance is, again, the voltage drop over the terminals divided by the current flowing into the network, or V over I. So our test source method is then applying a test source, either a voltage source or a current source, it does not matter which, to our dead network, and then measuring the quantity. So let's use a voltage source. So I'm applying a voltage source. We'll discuss what value I should use in a moment. But it's very important that I apply it to a dead network, so I need to turn off all of my independent sources. So I turn off voltage sources by replacing them with short circuits. Let's get rid of these nodal voltages because I'm not sure that's the methodology that I'm going to use. And most of these are no longer valid. So I'm going to apply a voltage, V test, and I'm going to measure a current, I test, and the ratio of V test divided by I test will give me my Thevenin resistance. So let's figure out what's going to be our easiest methodology here. Our test current is going to flow into this node and it's going to split up. Some of it's going to flow through that 1 kilo ohm resistor. Some of it's going to flow through this 4 kilo ohm resistor. And those are the only two paths that it can branch off. So I'm going to do my nodal analysis trick, as it were, again, where I'm understanding that when I turn off my voltage sources, I only have, this is a nodal voltage, which is going to be V test. This is connected to ground. All of this is connected to ground. So this is my only unknown voltage, V2, right here. I'm going to choose to use a 1 volt source because the homogeneity property of superposition tells me that it doesn't matter what voltage I use, I could just simply scale the result, so it's not going to matter. And so, applying Kirchhoff's current law at this node 1, I find that I test is equal to 1 volt divided by 1 kilo ohm plus 1 volt divided by 4 kilo ohms so that's 1 over 1,000 plus 1 over 4,000 is 1.25 milliamps. So our Thevenin is then equal to my test voltage, 1 volt, divided by my test current, 1.25 milliamps. Is again 800 volts. So we got the same answer we did before. Let's verify that it works if we use a current source. Let's choose a current source, direction up, 1 amp. We're going to be measuring this voltage drop, V test. So let's see, how can I do this in the most efficient manner possible? Well, I have a suspicion here, but I'm not sure if it's going to work. So this might bite me in the butt, as it were. So what my suspicion is that 1 amp of current from our test current source is going to flow into this node and it's going to split. The portion of it that splits through the 1 kilo ohm resistor will see this resistance kind of in parallel with this short circuit. And this guy will see, when it hits here, it'll see this guy and a short circuit. So I feel like that would work, but I'm not 100% sure that it can, I can say that it's not going to split. Effectively, I'm saying I think I could do this using simply current division, but I'm not 100% sure. I could do nodal analysis. So this is an unknown voltage V1 that will be the exact same thing as V test. This is an unknown voltage V2. And then this node is ground. This node is also connected to ground. This is a safer assumption. And so we would find that V1 over 1 kilo ohm plus, V1 is just V test. Okay, so let's set up our equations. So at node 1, we have 1 amp entering, so that's minus 1 amps, plus V1 over 1 kilo ohm, plus V1 over 4 kilo ohms is equal to 0. One equation, one unknown. We can solve this for V1. I get V1 is equal to 800 volts. And since this is equal to V test, then I get R Thevenin is V test, which is 800 volts, divided by I test, which is 1 amp, is 800 ohms. So whichever way we approach it, taking the ratio of the Thevenin voltage divided by the Norton current, applying a test voltage source or applying a test current source, we found that the Thevenin resistance was always 800 ohms. So these are the different methods that we can use to solve for Thevenin resistance when we have a dependent source. Just one thing that I want to make very, very clear. If you are applying a test source method, you have to make sure that you are looking at a dead network, which means before you apply your test source, which means only dependent sources are on, all independent sources are turned off.